So once we've collected all our data, then we need to find out, did our study actually turn out meaning anything? We collected it, we did an experiment or some correlations or whatever. But that doesn't tell us anything until we kind of analyze what we found. And we do that using statistics. Some of you might be taking statistics this year, or maybe you did last year. And statistics is basically, it's just a branch of math that looks at classifying and analyzing data. And it's not an end in itself. Statistics for psychologists are a means to an end. They're a tool. They're a very powerful tool to basically unlock some things within data that may be hidden without using statistical formulas. So they're an incredible tool that basically any practicing researcher must be very familiar with, and it's a really important part of really every psychology program. You have to take statistics classes. Psychologists generally use two major types of statistics. The one type is called the descriptive statistic, and the other is the inferential statistic. And they both have you use them in side by side in lots of different studies. There, you don't use like one or the other. They both play a role in pretty much all the research that psychologists do. So let's start with the descriptive statistics. These are really straightforward. These are they basically tell you what your data looks like. They describe your data in such a way that they can basically boil it down to a number. So therefore, there's descriptive statistics. The measures of central tendency, think of like if we had a test and someone said, Mr. Doyle, how did the class do on the test? I could use one of the measures of central tendency to distill the test scores down to a single number so you'd have a general idea of how people did. What type of statistics are we talking about? Well, one of the most basic ones that you're all familiar with is called the mean. Usually outside of statistics, it's called the average. It's the arithmetic average. It basically just means, you sum up all the data points and divide by whatever your n or your total number of points is. So there's your average. There's also the median. And the median is the score that falls in the middle. If you have an odd number of data points in your set, it's easy to find the median. It's, you put them in numerical order, and it's whichever one is right in the dead center. But if you have an even number of of data points, you don't have any number that's directly in the middle, so you take the average or the mean of the middle two. So if you had let's do 4 digits. Let's say we had a data set of 1, 7, 4, and 3. 1, 7, 4, and 3. We put those in numerical order, 1, 3, 4, and 7. And then our median would be the average of the middle two, the 3 and the 4. So the median would be 3.5, and that means half the numbers in that set are below 3.5, and the other half are above. That's what the median does. It tells you 50% is above, 50% is below that number. When would you use a mean and when would you use a median? Well, if you use a mean, just know that it's sensitive to outliers. If you have a really high number in a data set, it could make your mean look higher than it actually is. So just like if you had a test where, let's say, I gave a test to a class and most of the people in the class got in the 70s, but 3 people got 100. The mean of that test is going to look higher than the class actually did. It's going to be artificially skewed because there are, some outliers. Same thing could go the other way. What if we had a test where most people got in the 90s, but 3 people got a 50? That's going to bring the average down. So that also wouldn't be a good place to use the mean. That's where you'd use a median. A median is an excellent statistic to use when you have kind of a wide range of numbers and maybe some extreme highs or extreme lows, because it's not going to be sensitive to those, and it's not going to change. When you see like house prices, for example, like real estate values, they never talk about the average price of a home in, say, Quincy. They always and pretty much only talk about the median, because, you know, if most houses are in a certain range, but like then you have some, you know, Tom Brady moves into Quincy and buys a $25 million home, it makes the average look a lot higher. Or a very low price house will make the average look a lot lower. So they use the median. And then finally the mode, which is probably the most simple statistic of all. It's the most common score. So like, let's say you had a test and 7 people got an 83. And that's the most common score on that test. No other score is as common as the 7 different people who all got an 83. So that would be your mode. You'd say the test is, the mode of that test is 73. You can have a test that's, or a data set that is what you call bimodal, where you have 2 modes. So let's say you had a test where 6 people got an 85 and 6 people got 73. And those are both tied for the most common score. Well, that would be, we'd call that bimodal. You can also have trimodal and probably any other type of modal. Okay, so these measures of central tendency can tell you something, but they can't tell you everything. Imagine you have 2 classes, both of them have an average of 85 on the test. Okay, it sounds like they did equally well. It sounds like they all learned the material equally well. But what if you find out that one of those classes, that 85, ranged from a 60 all the way up to a 90, and a lot of things in between. And then you had the other class with an average of 85, and the range in that class, what if it was only 80 to 90, and everyone scored within that narrow range? Well, that's where measures of variability come in. They're a very important part of stats, and they help us to figure out even more about a set of data. The most basic measure of variability is the range. It's basically the highest minus the lowest score. So if you had, let's say the highest score in a test was a 97 and the lowest score was a 77, you'd have a range of 20. 97 minus 77. But a far more powerful statistic is called the standard deviation. The standard deviation tells us the average amount that each score in that data set varied from the mean. Okay? The average amount that each test varied or deviated from the average of that test. So let's say those two, so in other words, how much do the scores on average vary from the mean? Okay, and disregard that formula, that's a typo. You don't need to know it anyway. So how much do they vary from the mean? Let's take a look at another, let's look at standard deviations by taking a look at the normal distribution. The normal distribution, you may know as the bell curve, but that's really not the technical explanation or term for it. It's the normal distribution. All right, and the normal distribution is something. It's more or less theoretical. It doesn't necessarily exist in real life. But if, let's say, we took like IQ scores of people in the United States, as you get more and more people with their IQ score, you would expect the graph that results from that to approach what looks like the normal distribution. This normal distribution, the y-axis, the vertical axis, shows you how many people scored at a certain amount, and the x-axis is scores. In this particular case, it shows you standard deviations. So that 0, that the peak right in the middle there, that shows us really three things. The hump on the bell curve there is the median, because half of the numbers are above and half are below. It's also the average. It's the mean of all the numbers, all the people in that set, whether it's test scores or IQ or shoe size or height or weight. And it's also the mode. So it's the mean, median, and mode. The middle point of the normal distribution is the mean, the median, and the mode. And take a look at the 0. The 0 right down the middle there, along the bottom, right in the center. The 0 means 0 standard deviations. Okay, so imagine this is like the SAT. All right. The average SAT score would be the hump there at the peak. And then as you go out away from the mean, like higher than the mean, so let's say the mean's 500, and one standard deviation out, let's say it's 150. So 650 would be one standard deviation above the mean. Okay? 350 would be one standard deviation below the mean. All right? Now that those standard deviation numbers on the x-axis there, the -1 through 1, those numbers, let me, from here to here, these numbers, or this area, equals one standard deviation above it through one standard deviation below, and that accounts for 68% of your data. On a normal distribution, 68% of all scores will be within one standard deviation of the mean. As you can see, it gets much harder as you go out toward the distances, towards the extremes. So take a look here. Here's one standard deviation. Take a look at two standard deviations. If you go from 2 up to 2 above to -2, now you're accounting for 95% of all the scores. So 95% of all scores on a normal distribution are going to be within 2 standard deviations. If this is an IQ test, the most commonly used IQ test in the United States has a mean of 100 and a standard deviation of 15. That means 115 would be a standard deviation above. 130 would be 2 standard deviations above. I'll write those numbers in. Here's 130. And then going below, it would be 70. Oops, sorry. I gotta erase that. That's 85 and 70 would be 1 standard deviation below and 2 standard deviations below. So of everyone who takes the standard IQ test, it's actually the Wechsler Adult Intelligence Scale, 95% of every single person who takes that is going to get a score between 70 and 130. In order to score higher than that, you know, to get into the so-called genius level, very, very, very few people will be able to reach 3 standard deviations out. Look at this. So 99.7 accounts for 3 standard deviations above and below. 99.7 minus 95 is what you're talking about as the number of people in these tails. So that would be basically 4.7 divided by 2. That is how likely it is to score 3 standard deviations out. Once you hit 3 standard deviations out, you're accounting for almost every single person who takes that test. This would also be true of all kinds of psychological measures, whether it's weight, height, not weight and height are not psychological measures, sorry. IQ, self-esteem scores, numerical ability, how outgoing people are, how nervous people are. All of those things will conform to the normal distribution. The more people you get, the more numbers you get. Now, another important descriptive statistics we saw when we talked about correlation research methods is a correlation coefficient. Super, super, super common in psychology. Correlation coefficients are basically a way to describe a relationship between two variables. Say like how many hours a week you study and your GPA. Okay, that's like the common one I always use because it makes a lot of intuitive sense. The more like you collect the data from all your students, how many hours a week you study, and then find out what's your GPA at the end of the term, and you get a relationship described in that one number. The correlation coefficient, that number, is going to be expressed in a range from -1 to +1. And you express it by the variable r. All right. A positive correlation, if it's on the positive side, that means as one variable increases, the other increases. So the more hours you study, you would expect GPAs also to increase. Likewise, as one variable decreases, you'd expect the other one to decrease. So in other words, they both go in the same direction. As your hours of studying decrease, as those numbers go down, so do GPA scores. So that's a positive correlation. Negative correlation are what you could call an inverse relationship. This is when you have, as one variable goes up or increases, the other one goes down. Okay? So let's say the amount, a common one for this, the amount of time you spend, on TikTok, on your phone, the number of hours you spend on TikTok or any kind of social media thing, I would expect, and probably most people would expect, your GPA to go down. The more time, as that variable goes up, the other one goes down because you're not studying. Now, the closer to this is the absolute value of 1. The closer you get to the absolute value of 1, whether it's negative or positive, the stronger the relationship. So what do we mean? We mean, for example, a correlation of -8.7. I'm writing with my finger on my touchpad, so it's kind of messy. A correlation of -0.87 is more as a stronger correlation than, say, positive 42.42. All right, this one is a stronger relationship because why? Because it's closer to the absolute value of 1. As you get closer to 0, then you show a weak relationship. And a correlation of 0, if you actually had a correlation of 0, that would mean there is 0 relationship whatsoever between the two numbers. That might be, how would you ever have a correlation of 0? Well, maybe it's the length of your, like how long your street is in feet, like the street that you live on. How many feet is your street? And how many letters are in your last name? That I would expect that to be, 0 or pretty darn close, because they don't have anything to do with each other. Now, here are some graphs to kind of give you an idea of what these are going to look like. So this is a perfect positive correlation. R, the correlation coefficient, equals +1. So we'd call that a strong, and we'd actually call, if it's actually 1, we'd call that a perfect correlation, which in psychology you never see. It's more used for demonstration purposes and theoretically, but it would look like this. It would look like a 45-degree angle. As one variable goes up, let's say this is like GPA. Oop, that's really messy. GPA, and this is hours studying. I'll just put hours. All right, GPA and hours studying. As one goes up, the other one goes up. All right, and it's going to look something like that. In the real world, that graph wouldn't be perfect like that. It might be more, more like that. But that's also positive. Anything that kind of goes in a upward direction from the lower left to the upper right is going to be considered a positive correlation. Let's look at a negative correlation. So negative 0.95. This is also going to be a very strong correlation, but in this case it's negative. This is a strong negative correlation. Very strong. And what do you think it's going to look like? What do you think the graph would look like? If you guessed that it would look like kind of a mirror image of the graph above, you would be correct. It's going to look something like that. It's not quite 45 degrees, but pretty darn close. What about correlation coefficient of negative 0.33? That's a moderate correlation. We'd also say that that's negative because there's a negative sign at the beginning. And what is this graph going to look like? It's going to look like this one here, but not as steep. It's going to look like that. All right. Here are some other examples of some correlations for you. So the longer the lecture, the more you yawn. All right. These are the data points. So let's say, and because this is how they work, you have these dots that represent each person. The number of yawns, so this person was like right in the middle in yawns, and the lecture was not that long, so they're here. This person here yawned a lot, and the lecture was pretty long, and you can see the trend goes in this direction. All right. Where do we get this line? You may be wondering, like, how does that line get drawn? Basically, it's there's a term used in statistics. It's kind of a grammatically awkward phrase, but it's goodness of fit. You basically take the line that is as close to all the dots as possible. So if you move that line either up or down, it's not going to be as close to each other dot as it could be. So it's the line that literally is closest to all of them as it can be to represent them. Here's another one. The more you study, the higher your test grade. Kind of what I've said earlier. Hours of studying, as that goes up, test grades go from low to high. And it looks really similar to the yawning and the length of the lecture. Those are both positive correlations. Now, how about a negative correlation? The longer the lecture, the lower your attentiveness. So here's the length of the lecture, how attentive you are from low to high. If it's a really long lecture, you're very low attentive. If it's a shorter lecture, you have more attentiveness. Number of parties you go to and your test grade. The more you party, the lower your test grade. Remember that one. So this is another negative correlation. All right, so here are some others. So what kind of relationship does this graph show? I'll give you a second to look at it. Take a look at that graph. What is that, negative, positive, or no relation? It's hours of video games played and your GPA. You can probably tell that that is a pretty good negative correlation. It would even be stronger if this dot here, this is a bit of a little bit of an outlier, and the correlation would be even stronger, but we don't throw data out just because it's inconvenient. Here's the next one. What kind of relationship is this? So here you see the size of your television and the average time spent watching TV in a week. Now, in this case, that looks like a cloud of dots, and that is a classic example of no relationship. It's going to be pretty much a flat line. Although, I think these variables probably aren't accurate. I bet if you have a huge TV, I bet you watch more. I don't know. That's just me. And then what about this one? What kind of relationship? Hours spent studying. We already talked about this. And grade point average, you can see it's pretty obvious. It's totally obvious that these are forming a kind of a line that goes up. That is a pretty strong positive correlation. All right. So those are the descriptive statistics. They tell you what's going on in your data. But there's a whole other type of statistic that psychologists use all the time, and these are known as inferential statistics. And they do something different. They tell you whether or not your results are significant. What do we mean significant? And significance in this case is a technical term. It doesn't mean like a lot. It's not like the everyday use of significant. So if you read that as the results are significant, that doesn't mean the results are important. No, it doesn't mean that at all. It means this. Significant differences, remember, that's a technical term. Significant differences mean they are statistically unlikely to occur because of chance alone. You know that just based on chance, these are unlikely. In other words, this was not a fluke. There was really something going on. Okay? And that is going to wrap up this lesson. This is really all you need to know for the inferential statistics. You don't necessarily need to know specific types. That's for more at the once you take a stats class in college, then you'd learn them. But for the AP class, you don't need to know them. Okay, thank you for watching, and please let me know if you have questions on any of this.